Hello friends, now we are seeing what is the potential energy of an electric dipole in a uniform electric field. We already learned that when an electric dipole is placed in a uniform electric field, it experiences a torque, and the torque is trying to align the dipole parallel to the electric field. Let us consider this situation. Here we are placing a electric dipole. This is a uniform electric field. Suppose this is a uniform electric field in this region having magnitude E and directed in this directions. Here we are placing an electric dipole. Suppose this is our electric dipole. This is an electric dipole. This is negative charge, this is positive charge, plus Q, and this is minus Q. Say the length of the electric dipole is 2A, and 2A is the length, and its dipole moment is P. The dipole is aligned in such a way that its dipole moment makes an angle theta with the direction of uniform electric field. We know that the forces are acting for the charges in this uniform electric field. This positive charge experiences a force QE towards this direction, and this negative charge experiences a force in this direction, the same QE. But you see, these two forces are equal in magnitude, opposite in direction, but the line of actions are different, so they act a couple of forces, and which produce a torque. We already derived this expression. The torque acting on this dipole is equal to what? The torque acting on this dipole is equal to P cross E. P cross E, or can also write as torque is equal to PE sine theta. What is theta? Is the angle between the electric dipole moment and direction of electric field. Torque is equal to PE sine theta. P is the magnitude of dipole moment, E is the strength of electric field, and theta is the angle between the P and E. The tendency of this electric dipole is to align along the direction of electric field to minimize the torque. Suppose we are trying to change the position of this electric dipole by applying a small external torque. By applying a counter torque, we are trying to change the alignment of this dipole in this uniform electric field. And if you are changing the angle theta to another angle, say theta to theta plus d theta, that is the present angle is theta, we are increasing the angle to theta plus d theta, where d theta is a very small angle. So torque is trying to align this dipole along this uniform electric field. So we have to apply some external torque to change this angle, to increase this angle. So what is that work? We can write as the work required dW. The small work required for that process is equal to dW is equal to the minimum torque required for that process into the angle through which we turned. That dW is equal to torque into d theta, where torque is equal to the minimum. We required this much torque, PE sine theta into d theta. So we are writing as the small work required for that process is equal to dW is equal to, substitute for torque, torque is equal to PE sine theta into d theta. This much work is required. But actually, this is the work for changing by a very small angle or turning through a very small angle d theta. Suppose our aim is to turn it from an angle theta 1. Suppose we are trying to turn from an angle theta 1 to theta 2. This is work for turning through an angle d theta. How can you find work for turning from an angle theta 1 to theta 2 is you have to just integrate this dw. That is, the total work done is equal to integral dw. That's equal to integral an angle theta 1 to theta 2 Pe sin theta d theta. Pe sin theta d theta. This is the total work required for that process to turning an angle theta 1 to theta 2. So we can write the total work is equal to W is equal to, okay, integral P and E are constant. So we are taking it outside. P into E is a constant. From an angle theta 1 to theta 2, from an angle theta 1 to theta 2, sin theta d theta. Doing the integration, we know that integral sin theta d theta is minus cos theta. So work is equal to, keep Pe and within the bracket, square bracket, we are writing minus cos theta. Integral sin theta d theta is equal to what? Minus cos theta within a limit theta 1 to theta 2. So work is equal to P into E. Upper limit, usually we are writing upper limit minus lower limit, that is minus cos theta 2 minus cos theta 1. And we are multiplying with the minus sign. So we are getting like this way, P E cos theta 1 minus cos theta 2. This is the work done when you are rotating the dipole from an angle theta 1 to theta 2. Usually this work is stored as potential energy. So the potential energy of the dipole will be changed when you are turning from an angle theta 1 to theta 2. So this equation can use to calculate what is the change in potential energy when you are turning the dipole from an angle theta 1 to theta 2. So if you want to calculate what is the potential energy at a particular point or at a particular alignment, suppose initially the dipole is perpendicular to the uniform electric field, that you are taking theta 1 is equal to 90 degree. And suppose you are turning to another angle theta 2, say theta 2 is equal to, say you are turning to an angle theta from vertical position to another angle theta. So we are taking theta 1 is equal to 90 degree and theta 2 is equal to what? Theta. So what is the work required for that process? The work is equal to Pe into bracket cos theta 1 cos 90 minus cos theta. Cos 90 minus cos theta. What is cos 90? Cos 90 is 0 and say minus cos theta is the. So work done is equal to what? Minus Pe cos theta. Minus Pe cos theta. At all, thus work will be stored as potential energy. So potential energy of the dipole, we can write it as potential energy of the dipole is equal to minus Pe cos theta. Minus Pe cos theta, or it is equal to what? P dot E. Minus P dot E. Potential energy of a dipole in a uniform electric field is given by minus P dot E or minus Pe cos theta. Let us see at what alignment or at what position the potential energy of the dipole is minimum and maximum. Suppose if the angle between the electric field and dipole moment is equal to 0 degree. That is, in this expression, suppose we have theta is equal to 0. What theta is equal to 0 means the angle between electric field and the potential, electric dipole moment is 0. That is, dipole is like this. If this is the direction of electric field, if this is the direction of electric field, what the alignment of dipole? Dipole is parallel to the electric field. This is negative charge, this is positive charge. This is the direction of P and this is the direction of E. P and E are parallel. If P and E are parallel, what is potential energy? Angle is 0, minus PE. That is potential energy is equal to what? Minus PE. This is the minimum value of potential energy. If the potential energy is minimum, then we can say it is having more stability. The dipole is more stable if it is aligned parallel to the electric field. So this position, that is theta is equal to 0, at this position, usually the dipole having minimum potential energy, and we calling this alignment of the dipole as the stable. It is at a stable equilibrium position. Stable equilibrium position. Stable equilibrium position. We calling it stable as its potential energy is minimum. We calling it is equilibrium because net force acting on the dipole is 0. This is the stable equilibrium position of the electric dipole. What is it? The dipole is aligned parallel to the uniform electric field. And see, second case, if theta is equal to 90 degree. If theta is equal to 90 degree, how dipole is aligned? Suppose this is uniform electric field and dipole is parallel to the, perpendicular to the electric field. Here this is negative charge and this is positive charge. This is the direction of P. This is the direction of E. P and E are perpendicular to each other. It means what is potential energy? U is equal to minus PE cos 90. What is cos 90? U is equal to 0. Potential energy is equal to 0. So this position, the potential energy of the electric dipole is 0. Now we calling is the 0 energy position. We calling this position as 0 energy position of the dipole. 0 energy position of the dipole. If the dipole is perpendicular to the electric field, the potential energy of the dipole is equal to 0. So one more position, suppose if theta is equal to 180 degree. Theta is equal to 180 degree. How dipole is aligned? Suppose if this is uniform electric field, this is uniform electric field, and how dipole is aligned? This is negative charge and this is positive charge. Dipole is anti-parallel to the uniform electric field. This is the direction of dipole moment and this is the direction of electric. P and E are opposite in direction, anti-parallel. So theta is equal to 180 degree. So what is potential energy? You can say potential energy U is equal to what? Potential energy U is equal to minus PE into cos 180 minus PE into cos 180. Now what's cos 180? Cos 180 is minus 1. So it becomes plus PE. Potential energy is maximum. It is plus PE. That is, if the dipole is anti-parallel to the electric field, potential energy is what? The maximum. The maximum potential energy is P into E when the dipole is anti-parallel to the electric field. And so we call it is quite unstable equilibrium. This is known as what? Unstable equilibrium. We calling it as an unstable equilibrium position of the dipole. Why it is unstable? It is having maximum potential energy. First case we call is a stable equilibrium. Why it is stable? Because it is having minimum potential energy. When the dipole is parallel to the uniform electric field, it is having minimum potential energy and it is stable. That's why stable equilibrium. We calling it as equilibrium as the force is 0. Stable because it is having minimum potential energy. What is the second case? If it is perpendicular, if the dipole is perpendicular to the field, potential energy is 0. 0 potential energy position. 0 energy position. And the last case, if anti-parallel, if the dipole is anti-parallel to the electric field, potential energy is maximum. That's we calling unstable. Equilibrium we calling as its force acting on the dipole is 0. That's why equilibrium unstable as it having maximum potential energy. So that is the expression of dipole's potential energy in a uniform electric field.